Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So let's move to the third part of semiconductor. That is what we call extrinsic semiconductor. So in the previous video, we learned about intrinsic semiconductor. So this means by pure. There is no additional element. So if let's say the semiconductor is silicon, so you only have silicon around. Okay. So what is the problem of this intrinsic semiconductor? How you can get the current from this intrinsic semiconductor? You need to have enough energy to break what? To break the covalent bond. So how you can do that? You're going to apply heat at your semiconductor, and then the covalent bond will be broken once you have enough thermal energy, and then you can get a free electron, and then you can get the current. So the limitation of this intrinsic semiconductor, your current will be very small. It will be very small, and it's not enough to allow the electronic circuits to work. Okay, so that's why we need what we call extrinsic semiconductor. So this is the explanation. For intrinsic, it is very pure, and when it's very pure, in order for you to have the current, you need to break the covalent bond. So but it is not easy to break the covalent bond. That's why it leads to the small current flow. So how are we going to increase the current flow? We are going to increase what? Increase the number of free electron here. You're going to increase the number of free electron or hole. Why we need to increase the number of free electron? Because you want more current, means you want the semiconductor to be more conductive. So how we can do that? You're going to add specific impurity. What does it mean by impurity? So let's say the pure one is silicon. So you're going to add another material here at one side of both sides in order to increase the current flow, in order to increase the number of free electron. So this process, by adding the specific impurity atoms, we call doping process. By having this doping process, the semiconductor will be called as extrinsic semiconductor. Okay, so how you define extrinsic semiconductor? You are going to add by doping process, you're going to add selective impurity to the pure semiconductor. Means this is your pure semiconductor. You're going to add something to become extrinsic. Why you need this extrinsic? To increase the number of carrier. What does mean by carrier here is either it is a free electron or free holes. Why we need this free electron and free hole? Because you want more current. So what you're going to add at this on the pure, this A item, is either the impurities can be either from group 5 or group 3. So as you know, your silicon is group 4, right? Here is silicon. So the impurity comes from group 3 or group 5. Okay, so this is again the periodic table of the elements. So where is your semiconductor? Semiconductor exists at the group 4. So in order to have extrinsic, you need to add the pure semiconductor, the intrinsic, with either group 3. So what is the example of group 3? Is boron, aluminium and gallium. Or you're going to add with group 5. So what is group 5 here? Is either phosphorus or arsenic. So both group 3 and group 5 play a role to increase what? To increase the number of free electron and free hole to have more current flow. Okay, so this is the extrinsic semiconductor. We have two types. One what we call N-type, another one we call P-type. So silicon alone is intrinsic pure. So we're going to add the impurity. So the process is called doping. So why you add group 5? What is the example of group 5? Is the phosphorus and arsenide. And then when you add group 5 with your intrinsic, you can get N-type semiconductor. Okay, so let's see what happened when you at the impurity of group 5 for the pure semiconductor. So let's say here you have silicon, okay. You're going to dope this one with group 5. So example of group 5 is actually phosphorus or arsenide. So this is, let's say I choose this one, phosphorus. So you know what is the valence electron for your silicon? So you have here 1, 2. How are you going to draw this one? Let me have a clean. So now we are going to show you the n-type. So your n-type, how you can get your n-type, silicon plus group 5. So your silicon, I will draw only the valence electron. So you have only 4, 1, 2, 3 and 4. So you're going to dope this one with group 5. So let's say here we have 5 here. So this is phosphorus. So you have how many valence electron? Here you have 1, 2, 3, 4, and you have extra electron here. So next with the phosphorus, you have another silicon here. So you have 1, 2, 3, and 4. So if you see here, there is extra electron on top here. So this is what we call free electron. So imagine this one is replicate many times. So you have silicon here, you have phosphorus here. So you have a lot of free electron in your n-type. So by doping your silicon with the phosphorus, you will get a lot of free electrons. So there's come the keyword here, majority carrier. So this is the majority carrier. So you have a lot of free electron everywhere here. So when there is a lot of free electron, what is the majority carrier? So your majority carrier is electron. Okay. Minority carrier will be holes. So it is a donor impurity or acceptor impurity. So imagine this one. Since you have extra here, the yellow one here is extra. So here is trying to donate because your phosphorus here is having extra 1 electron here. The rest will be bounded at the orbit. So when you have free electron, it's trying to what we call donate. So we call the term here donor impurity is equal to, this is a donor impurity is a phosphorus. So when for n-type, we call donor impurity. Majority carrier is electron and the minority carrier is hole. Okay, so the explanation is here. So when you have n-type semiconductor, means you are going to dope pure silicon with group 5. So what is group 5? This either can be phosphorus or arsenide. So you have extra free electron here. This minus is not attached at the covalent bond. So this is what we call free electron. So imagine this is multiplied by many times. So you have a lot of free electrons. Okay. The free electron is free to move. So it will lead to current flow. So there are 3 terms here. The first term is the majority carrier. What is the majority carrier here? Because this is a free electron, right? So it is electrons. Minority carrier is the opposite hole. And the third term here that is important for n-type is donor impurity. Why we call this one donor? Because it has extra here. Let's say there's another free electron here, another free electron here. So when it have extra, it's trying to donate. So that's why we call this one donor impurity. So in order to have n-type semiconductor, we need to dope your pure semiconductor with group 5. That is phosphorus or arsenide. Okay, let's go to the next extrinsic semiconductor, that is p-type semiconductor. So for your p-type semiconductor, you're going to, instead of group 5, you're going to dope with group 3. So group 3 add with your pure semiconductor, you're going to get p-type semiconductor. Okay, so for p-type semiconductor, let's say here is your silicon. So you have 1, 2, 3, 4 valence. You're going to dope with group 3. Example of group 3 is boron. So what is the valence of boron semiconductor? You have only 3 valence, 1, 2, and 3. And next to the boron, again you have another silicon. Here also silicon, and here also silicon. So you have 4, 1, 2, 3. So if we see here, there is a hole here. There is no electron here. So this is what we call free hole. When there is a hole and any free electron that is somewhere here, it will go to the hole. So when there is a hole, there will be movement of free electron and there will be a current. So this is what we call p-type. So how we can get p-type? Silicon add with group 3. Example of group 3 is boron. And then you can get your p-type. So term number 1, majority carrier is equal to, so there will be a lot of hole inside your p-type. So the majority carrier is hole. Minority carrier is the opposite electron. Term number 2. So this is, it have empty here, right? A hole. So it's trying to accept. It lack one electron here. So it's trying to accept. So we call this one acceptor impurity. So what does it mean? The boron is actually acceptor impurity because there is a free hole here. So it's trying to accept any electron to go inside the hole. Okay, so this is the explanation for p-type. So you're going to dope with group 3. So while adding with group 3, it will create a hole. So where is the hole here? Here is a hole here. There is no electron inside. So the majority carrier will be hole, minority will be opposite. Why we call this one acceptor? Because it's trying to accept any free electron to go inside the hole. So by doping silicon with group 3, you will got p-type semiconductor. How about n-type? By doping group 5 with silicon, you're going to have n-type. By doping group 3 with silicon, you're going to have p-type. So both we call extrinsic semiconductor. Okay.